Alright, silly people, here's the situation. We have this potential minus h bar squared a squared over m such squared ax, and a trial wave function psi naught equals a such ax, and we just need to check that this is actually a solution to the Schrodinger equation as well as um, normalize it. And then after that, there's a kind of a completely separate problem. So it's kind of two problems in one. But yeah, let's just get into it. So the Schrodinger equation is looking like minus h bar squared over 2m del squared psi 0 del x squared um, minus h bar squared a squared over m such squared ax um, times psi 0 equals e psi 0. Um, so I'm going to write both sides of the equation because it'll help to cancel stuff out as we go. Um, so this is going to be a such ax minus h bar squared a squared over m a such cubed ax equals e a such ax. And I'm going to go ahead and cancel out all of the factors of a because we can. And then this is a derivative I didn't know off the top of my head, and so I'm betting that you don't either. But the derivative with respect to x of the hyperbolic secant or sech of x is just equal to minus sech x tanh x, right? So we're going to use that. We've got minus h bar squared over 2m, just doing the first derivative will give us plus a sech ax tanh ax. Yeah. And now the potential term is just sech cubed ax, and then on the other side, just e sech ax. So doing the second derivative, uh, splitting it up, we've got sech ax times the derivative with respect to x of tanh ax plus tanh ax times the derivative of sech ax, and then the potential term equals the right hand side. Again, the derivative of tanh is not one that I knew off the top of my head, so I'll write it out. It's del x of tanh x is actually equal to sech squared x. So that's fun. So now we have, and there's supposed to be an a here, h bar squared a over 2m, and this is going to be a sech cubed ax, and this is going to be minus a tanh squared ax sech ax, right? So it looks like now everything in the equation has a sech function attached to it, so we'll cancel a bunch of sech functions. And then also move this potential term into the brackets by multiplying it by 2. So we have a sech squared ax minus 2 sech squared ax Also factor out an a, so I don't have to write this a here. And then plus, no, this is still minus tanh squared ax equals e. And so carry out that subtraction and then factor out a minus sign. You get just sech squared ax plus tanh squared ax equals e. And then this is actually a trig identity, but the sum of sech squared and tanh squared is 1. So we just have that e is minus h bar squared a squared over 2m. That was relatively painless. To normalize it, we just have that we set 1 equal to the mod squared, or the integral of the mod squared of the wave function. So this is a squared integral sech squared ax dx. And then we know that the integral of sech squared is tanh, so you get a squared over a, just the tanh of ax, and this is from minus infinity to infinity. Tanh kind of looks like, it's kind of funny, but it kind of looks like this, where this is 0, and so it kind of has hyperbolic, or it has asymptotic, it kind of just goes to positive 1 for x equals infinity, and minus 1 for x equals minus infinity. So we're just going to have that it's a squared over a times 1 minus negative 1, so plus another 1. That's 2. So we find that a is just 2 over a. No, it's a over 2. Haha. But yeah, a over 2 under a square root. That's chill. So the next bit is now entirely, has nothing to do with that. Griffiths gives us a new wave function, psi sub k of x, which is a times ik minus a tanh ax over just ik plus a e to the ikx, where k is defined like roots 2me over h bar. And we have to check this against the Schrodinger equation, as well as talk about the transmission coefficient and reflection coefficient for this guy. So again, I'm going to write both sides of the Schrodinger equation on one big line, because it's going to be useful to cancel stuff out as we go. So it's minus h bar squared over 2m del squared del x squared a times ik minus a tanh ax over ik plus a times e to the ikx minus h bar squared a squared over m sech squared ax. That's the same potential as before, if that's not entirely clear in the problem statement. And this is over ik plus a e to the ikx. And there's also a that I forgot to write. And on the right hand side, it's e to the ikx times the funky little tanh function over ik plus a. So immediately we get a pretty good deal of cancellation, because all of these are proportional to a over ik plus a. So cancel all of those out. And then start doing the first derivative of the junk. So you're going to have a term which is just ik times ik minus a tench ax from the derivative of the exponent. And then you're also going to have a term which is the derivative of the stuff inside those parentheses, which is going to be minus a sec, or minus a squared sec squared ax. All of that is multiplied by the e to the ikx. So let me put in big parentheses e to the ikx. And then the potential term looks a little bit simpler. It's just ax times ik minus a tanch ax. We still have the exponential term, but that's going to go away eventually. And on the right-hand side, it's e times ik minus a tanch ax e to the minus ikx. And I don't think it's minus, actually. I miswrote it up there. Just ikx. Okay. So we're going to do the second derivative now. So we're going to have a term which is proportional to ik times all of that junk, which I just wrote. So ik times ik times ik minus a tanch ax minus a squared sec squared ax. Yeah. And then you're also going to have a term which is proportional to just the derivative of that junk. So plus ik, and it's actually minus a squared ik sec squared ax, and then the derivative of sec squared is going to be minus 2a squared sec ax times minus a sec ax tanch ax. Just a little bit of a chain rule integral, I guess. And then all of that is multiplied by the e to the ikx. And then we have the potential term. Ik minus a tanch ax to the ikx. And then we have the right-hand side. E to the ikx. So now everything has an e to the ikx attached to it, so let's cancel all of those out and start simplifying. So we have minus h bar squared over 2m, big brackets, minus k squared times ik minus a tanch ax minus ika squared sec squared ax minus a up minus ika squared sec squared ax, so the same term as that. That's fun. And then also minus 2a squared, and then this is a pretty obnoxious term, I guess, because it's plus 2a cubed sec squared ax tanch ax minus h bar squared a over m sec squared ax ik minus a tanch ax equals e times ik minus a tanch ax. Okay, So now that we have this, we're going to rewrite it in a pretty special way because you have that these two terms going to add up to 2ik squared, no, 2ika squared times such squared. This term is dependent on such squared. So we're going to group together all the stuff which is dependent on minus h bar squared a squared over m, and that's all going to be, and it's also all the stuff dependent on such squared ax. So it's going to be minus ik, uh, yeah, just minus ik plus tanh ax plus a tanh ax. That's a good note to have. Plus ik minus a tanh ax. So that's cool. Then we are going to take the k squared term out of there. So it's going to be h bar squared k squared over 2m times ik minus a tanh ax. And then on the right hand side, still e times ik minus a tanh ax. Okay. This term cancels out this term cancels out this term. So that whole thing is 0 now. And then we're left with the h bar squared k squared over 2m thing. And both that and the e term on the right hand side are multiplied by this. So we cancel those out as well. So we just have h bar squared k squared over 2m equals e. After all of that, we can expand the definition of k. So this is going to be 2me over h bar squared. So after all that, we get that e equals e, and we killed it. That's a valid solution to the Schrodinger equation. The next thing that Griffiths does is he looks at the asymptotic forms of the wave function. So he observes that psi sub k of x in the limit of x is really, really big, x goes to infinity, that he has it's a times ik plus a over ik plus a e to the ikx, because tanh of positive infinity is just positive 1. So he observes that it's a e to the ikx, very simply. Then he asks us to get the other asymptotic form of psi sub k of x for x goes to minus infinity. And then, so tanh of minus infinity is minus 1. So it's ik minus a over ik plus a e to the ikx. So that's what we're going to go with. And then he wants us to use this to get the transmission coefficient and reflection coefficient. So if you remember, the way that the transmission coefficient is originally defined is the ratio of the probability currents on either side of the potential. So we're going to do the probability currents for the x goes to infinity case, and the probability current for the x goes to minus infinity case, and then the ratio of those will be the transmission coefficient, right? So doing the top one first, so the probability current of x goes to infinity. If you don't remember, the probability current of anything is just I h bar over 2m times psi del psi star del x minus psi star del psi del x. So we've got I h bar over 2m psi is just looking like a e to the ikx. The derivative of the complex conjugate is looking like minus ika e to the minus ikx. Psi star is just a e to the minus ikx. The derivative of the wave function is just ika e to the ikx. So these two terms are the same. They'll add up. So it's just minus I h bar over m times a squared times ik. Yeah, fancy stuff there. Then the probability current in the other region, the x goes to minus infinity region, looks like I h bar over 2m. Psi was just a ik minus a over ik plus a e to the ikx. The derivative of the complex conjugate will look like minus ik times minus ik minus a over minus ik plus a times e to the minus ikx. And then the complex conjugate looks like a times minus ik minus a over ik plus a, or that's a minus sign there as well, times e to the minus ikx, and then the derivative of the wave function is just ik minus a, ik plus a, e to the ikx. Again, these two terms are the exact same. So the exponents all cancel out. We get minus I h bar over m times a squared. But then in here we just have it's like the square modulus of ik minus a over the square modulus of ik plus a, pretty much. So that looks like k squared plus a squared on the top, and also k squared plus a squared on the bottom. And there's also the ik term, which gets carried along. So those cancel out, and we just get minus I h bar over m a squared ik, which is the same as what we got up here, which means when we take the ratio of the two, we just get 1, which means that the reflection coefficient is 0. That just means that the wave function, whenever you pass it through from left scattering on into the potential, 100% of it is going to get through the potential. And that's a pretty interesting problem, I think. All right.